Assalamualaikum to all of you. Okay, so we're going to finish our lecture 25, which will be our last lecture for this course. Okay, so without further ado, let us proceed with lecture 25. So lecture 25 will be covering the topics of wave propagation in good conductors. Okay, and afterwards we're going to have a look at the wave power, particularly on calculating the wave power by using the Poynting Theorem. Yeah. Okay, so just recall back the topics that we have learned in this chapter, in the last chapter. Yeah, in this last chapter, basically, we are learning about we have learned about the wave propagation. And just to recall that we have learned about wave propagation in few materials, few environment, which include the free space, lossless dielectric, and also the lossy dielectrics. Yeah, so far. So this will be the last one, which will be the wave propagation in good conductors. Yeah. Right. So objective for this lecture will be similar to what we have learned previously. We just change the material. Yeah. So we're going to have a look on the wave propagation behavior in a good conductor. Yeah, in the good conductors in terms of intrinsic impedance. Okay, so we're going to see what should be the value of intrinsic impedance for the medium, yeah, for the good conductor. And afterwards, we're going to have a look at we're going to have a look at the wave velocity, yeah, wave velocity, and also the phase constant. Okay, and finally, we're going to have a look at relationship between the propagating electric field and the magnetic field. Okay, and the second objective will be on calculating the wave power by using the Poynting Theorem. Right, so just to recall back that previously we have learned about uh, the lossy dielectrics, I mean the wave propagation in lossy dielectrics, in which we have distinguished, yeah, we can differentiate the wave propagation behavior in a lossless medium and also in lossy medium. Yeah, for examples, if we have in a lossless dielectric, yeah, if we consider a lossless medium, for instance, if we assume that the wave is propagated in the z direction, for instance, and if we take the E field, let's say the E field is polarized, or E field wave is polarized in the x direction. So we're going to have an equation of E as E positive is the amplitude of cosine of omega t minus the kz in the direction of x. Yeah. So this is the general equations for the electric field in a lossless medium. If we consider the wave is propagating towards the z direction and the wave is polarized along x. Okay, if we consider the same case, I say if we consider the same, but let's say if you consider the medium is a lossy medium, yeah. So we're going to have a difference in which the E field can be written as E positive is the amplitude. So we're going to have an additional terms of reduced exponential, yeah, exponential of negative alpha z, which will effect on the reduction of the wave, yeah, and then we're going to have a cosine of omega t minus beta z, okay, and in the direction of x. Okay, and we have learned also that in a lossy medium, that the H field will be having about similar terms. Where we have the H positive exponential negative alpha z, cosine of omega t minus beta z, and we can see that there is a phase difference of theta eta, yeah, between the E field and the H field. So if we take that the E field is polarized along x direction, so the H field by right shall be polarized along the y direction. Yeah. Okay, and we can see that the difference between the E and H for a case of lossy medium is that the E field amplitude over the H field amplitude shall be equals to the amplitude of the impedance. So there's a formulation for the impedance, which is we have learned this in the lecture 24 before. Yeah, and also then we can have the theta is basically related to this equation of tangent of 2 theta equal to sigma divided by omega epsilon. Okay, so please check about this formulation. It's quite long. If I'm not mistaken, it's about mu over epsilon over something, 1 plus sigma over omega squared power of 1 over 4. If you're not mistaken, yeah, please check this formulation for the amplitude for the impedance. Okay, so basically these are the things that we have learned so far, yeah, in a lossy medium. For the case of lossless medium, I think there should be no problem at all because we're going to have about similar equation, okay, minus kz direction of y, and in which for the case of lossless medium, the E and H amplitude, the amplitude of the E and H can be related by the same method, which is the ratio between the E and H amplitude should be equals to the eta, the impedance, and the impedance for the case of lossless medium should be based on the equation of mu over epsilon. Okay, so this is, I can say this is a summary from what we have learned in our previous lecture 23 and lecture 24. Yeah, and please check the formulations for the alpha and beta for the case of lossy medium, which is quite long. Yeah, but don't worry about that. So those equations will be provided to you. Yeah. Okay, so for now, we're going to proceed with the the next medium, which is a conductor. So we're going to see what should be the difference for the wave, which is said to be propagating in this particular good conductors medium. Yeah. Okay, so for that, let's have a look at this slide. We have learned previously that the alpha and beta, yeah? So this is the equation for the alpha and beta that we have learned in lecture 24, yeah, where the alpha and beta are basically related to the omega, yeah, or determined by the omega, which is the frequency of the wave, the mu, permeability, epsilon, the permittivity, and also the sigma, which is the conductivity of the medium. Okay, and we have learned in lecture 22 previously in topics of lossy dielectrics, in which we can classify that for a good conductor, the value for loss tangent, yeah? So remember that this is a loss tangent equation, yeah? Loss tangent, LT is loss tangent, is equals to sigma over omega epsilon, in which for the case of a good conductor, we have agreed that the loss tangent value should be very high. Yeah, should be very high for the case of good conductor. So we can see that for a good conductor, the value for the loss tangent is assumed to be much bigger than 1. Yeah, much bigger than 1. Let's say if we have 100 for loss tangent, we consider that to be a good conductor also. Yeah, 100, few thousands. Yeah, so that should be considered to be a good conductor. So if we apply this assumption in which the value of loss tangent is very much higher as compared to 1, if we substitute these terms in your alpha and beta terms, so you can say that there should be some modifications that can be recorded from this insertion, from this approximation of loss tangent, in which if we can substitute this value in the equation number 2, for instance, yeah. So if we substitute that value in the equation number 2, we can say that 1 can be ignored. Yeah, 1 can be ignored here because the value of sigma over omega epsilon is much bigger than 1. Yeah, so this value will be simply, we square root the value. So the results of this, yeah, will be equals to sigma over omega epsilon straight away. And minus 1, so minus 1 can also be ignored because the value is very small as compared to this loss tangent value. And then this will be then multiplied with the mu epsilon over 2, okay, and also we have omega, yeah, omega, we can have it as a square root of omega squared, yeah, omega squared, so we just have it as 2 pi f squared straight away, yeah, because we know that omega equals to 2 pi f, yeah. So when we bring the omega inside the square root, inside this square root term, we're going to have this. Okay, so a few things can be cancelled out here. So we can cancel out the epsilon. Okay, we can cancel out 2 here. Yeah, let me see. Okay, so we have 2 omega. So we have 2, okay. So end up going to have it as equals to, let me see, yeah. Okay, so we're going to have square root of 4 pi squared. Okay, right. Okay, sorry. We have 4 pi squared of f squared, yeah, mu sigma divided by omega, which is 2 pi of f. So a few things can be cancelled out still. So pi cancel out. So we have 2, sorry, this is omega, yeah. We're going to have 2 pi f. So we have 4 down here, basically. Yeah, we have 2 there. So this can be cancelled out with 4. So f can be cancelled out. So end up, we're going to have a simplified version of alpha shall be equals to third of pi f mu sigma. Okay, so this is a simplified version for the alpha for the case of a good conductor. So from very long equation for the alpha that we have used previously for the case of lossy dielectrics, we have then simplified it by simply assuming the value of loss tangent should be very high as compared to 1, and we have conclude that the alpha for the good conductor can be simply written as this value, where the alpha for a good conductor will be depending on the f, the frequency in Hertz, the permeability in mu, and the conductivity of the medium for the good conductor. And you can prove that by using a similar approximation for the loss tangent in equation number 3, we're going to have that the beta will be following the same alpha value. It means we're going to have the same equation, pi f mu sigma. So basically from here, we can see that for a case of good conductor, and it has been proved here that the value for alpha and beta will be similar for the case of good conductor, which is equals to third of pi f mu sigma. Okay, so this is a value for the alpha and beta. Alpha is adhesion constant and beta is the phase constant for the wave propagating in a good conductor. Okay, right. So, okay, this is what we have discussed in the previous slide. Yeah, so it has been shown here that the alpha and beta will be following the same value, pi f mu and sigma. Okay, and the same things shall be applied for the case of good, for the case of impedance. Yeah, for the case of impedance, in which we have this value for the impedance, basically. Yeah, equation number 6 is the impedance for the case of lossy medium. And for this impedance value, we can obtain it in terms of the amplitude of the impedance and the phase of the impedance. Yeah. If we can recall back previously, we have the value for the impedance amplitude for the case of lossy medium should be equals to, let me check. Yeah, so it should be equals to third of mu over sigma, sorry, mu over epsilon divided by 1 plus sigma over omega epsilon squared and 1 over 4. Okay, so if we take in a similar approximation for the case of good conductor, whereby the sigma over omega epsilon is very much bigger as compared to 1, and we substitute it into this impedance amplitude, we are going to have that the impedance basically will be giving us mu over epsilon. Okay, so this sigma over omega epsilon squared as compared to 1, so we can simply cancel the 1 value. Yeah, so end up going to have only sigma over omega epsilon squared. And square root for that, we're going to have square root of sigma over omega epsilon. And subsequently, going to have mu over epsilon multiply with omega epsilon over sigma. So this can be cancelled out and end up going to have only omega mu over sigma. So that should be the equation for the amplitude, magnitude for the impedance in the case of a good conductor. For a good conductor, the value for the impedance amplitude has been simplified only to have a square root of omega mu over sigma. Yeah, so it depends on the frequency omega, it depends on the mu permeability of the medium, and also on the conductivity. Yeah. And the same things apply for the theta, for the angle of the impedance. So we have theta basically based on the previous equation for lossy medium. So theta shall be equals to half arctangent of sigma over omega epsilon. Right? So this is the equation. It comes from tangent of 2 theta equals to sigma over omega epsilon. Yeah. And if we take a consideration whereby sigma over omega epsilon is very much bigger as compared to 1, so we're going to have that this equation can be written as theta as half of arctangent of infinite. Yeah, if we consider that the value of this loss tangent is very much bigger as compared to 1, so we can assume that to be infinite approximately. Yeah, and the arctangent of infinite will give us 90 degrees, and when divided by 2, going to have the impedance for the impedance angle shall be equals to 45 degrees. Okay, so evidently it shows that for the case of a good conductor, the value for the impedance has been simplified, where the impedance amplitude will be omega mu over sigma, while the angle for the impedance will be fixed at 45 degrees. Yeah, so this is the value for the impedance in a good conductor. I repeat again, magnitude is a set omega mu over sigma, whereas the angle of the impedance will be fixed at 45 degrees. Yeah. Okay. All right. So this is what we have obtained from the previous slide. So this is the equation for the impedance, and as such, we can then write the general equations for both the E and H field. If we consider that the field, the wave is propagated towards Z direction, okay, propagation in the Z direction, and the E field is polarized along X direction, while the H field is polarized along Y direction. So that should be the general equations that we shall obtain from equation 8 and 9. So we go for the equation 8 first. So we're going to have the EZ, yeah, which is the E field wave, will be E positive exponential negative alpha. Yeah, this is your alpha for the case of good conductor. Cos omega t minus beta Z. Yeah, whereas for the H field, we're going to have the H positive exponential negative alpha Z cos omega t minus beta Z with the phase difference of 45 degrees between the E field and the H field. Yeah, so always remember that the E field shall always lead the H field by 45 degrees in a good conductor. Okay, any questions for this explanation on the wave behavior in a good conductor so far? No, yeah. So basically, it's similar to lossy dielectrics behavior. But the difference will only be on the simplified versions of alpha, beta, and also the impedance. Yeah. Okay. Right. Before we proceed with the next topic, we just want to refresh on your understandings on the velocity. So previously, for the case of velocity in a lossless medium, we have that the velocity of v, which is the velocity of the wave, equals to omega divided by k. Yeah? K is your phase constant. So we have agreed on this, in which k for the case of lossless medium will be equals to set of mu epsilon. Yeah, this is the equation for your k. Yeah, the phase constant in a lossless medium. But for the case of lossy medium, the value for the velocity shall be equals to omega divided by beta. Yeah, beta is the phase constant, which is calculated using a very long equations that we have seen in the previous slide. And the same things applied for the case of good conductor, where the equation for the velocity should be similar to this equation where we have omega divided by beta also. But for the case of conductor, the beta equation, the beta terms has been simplified. Yeah. Okay, so this is the equations that shall be used in calculating the velocity of the wave. Yeah. Right. So next, we're going to have a look at the concept of a skin depth. Yeah, skin depth. Okay. Skin depth basically is related to the behavior of the wave that is propagating in a good conductors. Okay, so if we consider, for instance, yeah, if we have the E field wave of, in this particular equations, yeah, we have Ex positive, exponential negative alpha z, cos omega t minus beta z. Okay, so if we assume that this is your conductor, yeah, this is a good conductor, the blue color here, the blue rectangular color here. So if we assume that the initial amplitude of the wave once it's enter the conductor is given by E positive, for instance, yeah. So there is a distance, yeah, there's a distance in which the amplitude of this wave will be reduced to 0.368 out of the initial amplitude. Yeah, initial amplitude. So initial amplitude is E positive. So if we have a distance here in which the amplitude has been reduced by 0.368 of the initial amplitude. So this particular distance is what we call as a skin depth. Yeah. In other words, skin depth is a thickness or is a depthness in which the amplitude of the wave has been reduced to 1 over E of the initial amplitude. Yeah. So if we take these particular equations, if we take this is the amplitude of your wave. So 1 over E basically, yeah, if we have, let's say we have a distance of Z equals to 1 over alpha. Z equals to 1 over alpha. So when we have Z equals to 1 over alpha, we're going to have that the amplitude will becomes as a 1 over E of the EX positive. Am I right? Yeah. So if we substitute Z equals to 1 over alpha, yeah. So this is your alpha. So when Z equals to 1 over alpha, the amplitude of the wave will becomes 1 over E of the initial amplitude. So this is equals to 0.368 of the amplitude. Okay, so basically the skin depth is equals to 1 over alpha. Yeah, skin depth will be equals to 1 over alpha. So if we can see that if we are having bigger alpha, yeah, if you're having bigger alpha, so the skin depth will be smaller. Yeah, if you have bigger alpha, so the relationship will be bigger alpha are going to have smaller skin depth. Yeah, so if you have smaller alpha, skin depth will be increase. Yeah, so basically this is very important in a design. Yeah, in a design in which if you want to have if you want your device, for instance, if you want your device to be protected from the external wave, for instance, yeah, from the external wave, so you may need to design your material, yeah, such that you are going to have a very small skin depth value, yeah, very small skin depth value, so that the wave cannot simply penetrate your device. Yeah, so that should be basically depending on the alpha value. So you can tailor, you can design the alpha such that you can have your intended or your preferred value of a skin depth. Yeah. So a skin depth, in short, I can say a skin depth is a thickness whereby the amplitude of the wave has been reduced to 1 over E, yeah, 1 over exponential of the initial amplitude once the wave entered the conductor's medium. Yeah. Okay, so that's skin depth. All right, and this is what we have discussed just now about the skin depth, which is equals to 1 over alpha. Okay, and it can also alternatively describe as a distance, yeah, in the conducting medium, in which the amplitude of the wave has been reduced to 36.8% or just 37% of its initial value. Yeah, so this is another explanation for the skin depth. Yeah. Okay, I think that should be the important things to be discussed in this topic of wave propagation in conductors. So we can then proceed with these examples, yeah, to test our understanding on the wave propagation in a good conductors. Yeah. Okay. So for this example, we are given the electric field intensity of a linearly polarized uniform plane wave propagating in the positive z direction in the seawater, which is given by electric field E as 50 cosine 2 pi times 10 power of 7t in the direction of x at z equals to 0. And the constitutive parameters of seawater are relative permittivity of 72, relative permeability of 1, and the sigma of 4 Siemens per meter. Yeah. So we are given a case of electric field intensity wave, the field wave basically, which is said to be propagating in the seawater, which is propagating in a positive z direction as given in the question. And the equation is given by simply 50 cos 2 pi times 10 power of 70 direction of x. Yeah. So this is the value of E field at z equals to 0. And basically, we can also write that since this particular medium of seawater do have a sigma value, so so this medium can be a lossy dielectrics or it can be a good conductor. Yeah, so it can be either one of these. Yeah, whether it can be a good conductor or it can be a lossy dielectrics because we have the value of sigma there. Yeah, so we can also write that this is the value of z equal to 0 basically. But in general, you can write that the E field equation shall be equals to 50. So don't forget about the exponential terms. Yeah, the reduced exponential terms need to be there. Yeah, so for this particular case, we can ignore, we can omit it because this is at z equal to 0. So there should be no effect here. Yeah, so there is no effect on the amplitude, but in general, there should be effect of exponential negative alpha z in your E field wave equation. Yeah, and we have a cosine of 2 pi times 10 power of 7t, and still we have a phase difference, phase change of negative beta z, yeah, because for the case of at z equal to 0, this value can be omitted, yeah, but in general there should be a phase change of negative beta z, so that should be in the direction of x polarization, yeah, so that should be the E field in general that we have. Okay, so based on that, we need to determine, number one, the type of medium. Okay, so before we can calculate the important parameters required from these questions, for instance, the beta, the alpha, the impedance, we need to first find out what kind of material is this. Whether is it a lossy dielectrics or is it a good conductor, because it can be either one of these. So how to test it? So what you have to do is that you have to evaluate the value of loss tangent, the sigma over omega epsilon. So every time, if you want to classify the material, calculate its value first. Okay? You please calculate its value first, and after that, then only we can find out whether this material, is it a good conductor or is it a lossy dielectrics. So basically, from this given information, sigma will be equals to 4, omega will be 2 pi times 10 power of 7, and the epsilon should be equals to 72 multiplied with the free space permittivity, which is 8.854 times 10 power of negative 12. So what should be the value for this? So let us calculate the value for this loss tangent. Going to have a 2 pi. Okay, then we have power 7 times 72 and times 8.854 negative 12. Okay, let me see. 2 pi. Okay, and then we have 72, and then we have 8.854. Okay, and then we have the value should be equals to 99.86, which is about 100. Yeah, it's about 100. So 100 is considered to be bigger as compared to 1. Yeah, this value is bigger as compared to 1. So we can assume that this medium is a good conductor. Yeah, it's a good conductor. So the seawater is considered to be a good conductor at this particular frequency of 10 power of 7, yeah, Hertz. Okay. So because basically this particular loss tangent will be depending on the sigma and omega, yeah, and also the epsilon. And as calculated here, we have obtained a value of loss tangent of 100. So we can consider this to be a good conductor, yeah, as compared to 1. Yeah, so this is a good conductor at this frequency of 10 to the power of 7 in Hertz. Yeah. So number 1, the answer for this medium should be a good conductor. Okay, so when we have classified the metal to be a good conductor, so the rest, the alpha and beta, shall be based on the formulations of alpha and beta for the case of good conductor. For instance, the alpha shall be equals to sort of pi f mu and sigma, yeah, and this is also equals to beta, yeah, because the value for alpha and beta are the same for a good conductor. And if we calculated this value, we're going to have pi multiply with the frequency, which is 1 to the power of 7, and then multiply with the mu, which is 4 pi, yeah, 4 pi, yeah, 4 pi, 10 of negative 7, okay, and then multiply with sigma, which is equals to 4. And then you have to have the answer for that will be equals to 12.57. Yeah, so alpha and beta be 12.57. So please correct please recalculate it for me if you, maybe I'm doing something wrong here. Yeah, I'm doing wrong here. So maybe you can prove to me that the answer for this alpha and beta is correct. Yeah, so please calculate it back in case if I did anything wrong here. Yeah, so the alpha and beta is the same, which is 12.57 based on my calculation. Okay, and then we proceed with the value for the phase velocity and the intrinsic impedance. So for the phase velocity V, you're going to have the value of omega divided by beta. So omega is 2 pi times 10 power of 7, and the beta is 12.57, which is calculated above. So the answer for this velocity of the wave will be divided by 12.57. So the answer for that will be equals to 0.5, yeah? 0.5 times 10 power of 7 meter per second. So that should be the velocity of the wave propagating in this good conductor. Whereas for the case of impedance, the intrinsic impedance, the eta, okay, let us see whether we have a blank slide at the end. Okay, we have blank slide, yeah? So for the case of eta, the impedance, so that should be based on the amplitude, which is omega mu over sigma, with a fixed phase of 45 degrees. So that should be the amplitude of the impedance. You're going to have 2 pi times 10 power of 7 for the omega. Mu will be 4 pi times 10 of negative 7, whereas for the sigma will be 4, yeah, and that should be 45 degrees angle. So you're going to have the value of 8 pi squared divided by 4, so that should give us 2 pi squared as the amplitude, yeah, and the phase angle will be fixed at 45 degrees. So that should be the value for your impedance, yeah. So this impedance should be in the units of ohm, yeah. Right, so that should be the impedance for your medium. For the fourth one, which is the skin depth, yeah, skin depth. Okay, skin depth shall be based on the value of alpha. Okay, so the skin depth value, yeah, shall be equals to 1 over alpha. So that should be equals to 1 divided by 12.57. Yeah, so when we calculate this value, we're going to have 1 divided by 12.57. And the answer for this will be equals to 0.075 meter. And this is equals to 7.95 centimeter, which indicates that when the wave propagating at the distance of 7.95 centimeter, inside the seawater, the amplitude of the wave will be reduced by 1 over E of the initial amplitude. So basically, we have agreed just now that initial amplitude is 50, yeah, 50 is the initial amplitude. So we can say that this is the seawater, for instance. So the initial amplitude is 50 here, is 50, the amplitude. So at the distance of 1 over alpha, let's say we consider this is to be the delta, this is 1 over alpha. So the amplitude here has been reduced, yeah, has been reduced, sorry. So this amplitude, if we can have it as 1 over E or 50. Yeah, so the amplitude at this particular point, which is at this depthness of 1 over alpha, will be 1 over E of 50. 50 is the initial amplitude, so 1 over E is the reduced amplitude. Yeah, right. So that's how we determine the skin depth of the wave propagating in this seawater medium. And next will be on the wavelength. So wavelength, I think, should be straightforward answer. We have lambda should be equals to V over frequency F. So from previous slide, we have calculated that the V is 0.5 times 10 power of 7. Okay, so we have 0.5 times 10 power of 7 as the velocity of the wave, and frequency is 1 times 10 power of 7. So can be cancelled out, we're going to have only 0.5 meters. So that should be the lambda. Okay, and for number 5, the distance, yeah, the distance at which the amplitude of E is 2% of its value at Z equals to 0. Okay, so basically, we're going to calculate the amplitude of the wave. Okay, so we have, let's say this is a seawater. Yeah, this is Z, the distance of propagation. This is Z equal to 0. Okay, so the initial amplitude is 50. So the wave is propagating inside the medium. Okay, and you need to find out what should be the amplitude. I mean, what should be the distance in which the amplitude here, yeah, the amplitude has been reduced to only 2%. Yeah, 2%. So 2% of initial amplitude of 50. So this should be equals to what then? 2 over 100 times 50 will give us 1. Yeah, this should be equals to 1 volt per meter. So that should be the amplitude. Yeah, the amplitude which is 2% out of the initial amplitude. So we're going to have, we can find this distance. Let's say we find it as, we use Z0 here. Yeah, so we're going to have that 50 exponential of negative alpha multiplied with Z0 shall be equals to 1. Yeah, 1 is the amplitude, which is what, 2% from the initial amplitude there. So your aim is to find the Z0, yeah, the distance, yeah, the depthness. So you're going to have it as exponential negative alpha, which is 12.56, which has been calculated earlier. So Z0 equals to 1 over 50, which is 0.02, is it? 1 divided by 50 shall give us 0.02. Yeah, 0.02. And as such, you can use a Lorentz technique. Yeah, so you have negative 12.56 of Z0 equals to ln of 0.02. And as such, from here, we can have that the Z0, the distance, shall be equals to ln 0.02 divided by 12.56. So that should give us about 0.31 meter. Okay, and this should be equals to about 31.1 lah, yeah, 31.1 centimeter depthness. Yeah, so that should be the distance. Yeah, the distance inside, yeah, the distance of the seawater in which the amplitude of the wave, which is initially at 50, has been reduced to only 1, yeah, to only 1 volt per meter. So that should be the thickness, the depthness of the wave, yeah, the depthness of the seawater. Okay, is it clear on the solutions then? Any questions so far? If you have any question, please ask, yeah? I hope you understand this clearly, yeah? Okay, very good. Okay, and I think the last one is to write the expression for the EZT and the HZT at Z equals to 1 meter as a function of T. Okay, I think for this, we need to go back to this equation here for the case of the electric field. So we have the equation of E will be 50 exponential negative alpha Z, yeah, cosine of 2 pi times 10 power of 7t minus beta Z, okay, direction of X in volt per meter. So we can see that the alpha and beta is based on what we have calculated earlier, which is about 12.57. So that should be the value for alpha and beta, yeah? So I just use alpha and beta in this equation. So at z equals to 1 meter, what you have to do is that we just substitute the value of 1 in your equation for the exponential of negative alpha z and also on the negative beta z. Yeah, I don't think I have to do it for you, so you can do it on your own, yeah? So just substitute the value of alpha, the value of beta together with z equals to 1. Whereas for the H field, we are going to have supposedly, we can see that for the case of the H field amplitude, we have agreed that the E field amplitude over the H field amplitude equals to impedance of the amplitude of the impedance. So basically the H field shall be equals to 50 divided by the impedance amplitude, which has been calculated before this, which is what then? The impedance amplitude is 2 pi squared. Yeah, so we're going to have 50 divided by 2 pi squared. Yeah, 2 pi squared, that should be the amplitude of the impedance. Exponential of negative alpha z cosine 2 pi times 10 power of zt minus beta z minus 45 degrees. Yeah, there should be a phase change of 45 degrees between the E field and the H field. So don't forget about this phase change of 45 degrees, phase difference of 45 degrees. And for the H field polarization, I think if we know that the field is directed towards the Z direction, the E field is polarized along X direction, so the H field by right shall be polarized along Y direction. Yeah, I think you should know about this lah. Yeah, because we have learned previously that direction should be based on the E field polarized direction cross the H field polarized direction. So if your direction is Z, for instance, yeah, so the E field is in the X direction, so basically the H direction should be in the Y direction, yeah, because X cross Y will give a Z. Okay, so that should be the H field wave equation. Yeah, so in order for us to obtain the expression for the HZT z equals to 1, so similarly substitute the value of alpha, beta, and z equals to 1 in this equation of H field wave. Yeah. Okay, so that is the sample of an exam questions. Yeah, for the topics of a good conductor, wave propagation in good conductor. Okay. Right, so let's have a look at this example, next example, in which we need to calculate the skin depth of a copper at 60 Hertz and also at 6 gigahertz. Yeah, need to calculate the skin depth value. So basically this is to distinguish, to understand the effect of the skin depth related to the frequency of wave. Yeah. Okay, for instance, yeah, for the case of 60 Hertz wave, yeah, 60 Hertz wave, we have understand that the skin depth shall be related to the 1 over alpha, yes, 1 over alpha. So for this, we can calculate the alpha value should be equals to set of pi f mu sigma. Okay, so if we consider the case of wave at 60 Hertz, we're going to have pi multiplied with 60 as the f. Mu is considered to be just a mu naught because we have given here that mu r is 1. So that should give us 4 pi times 10 power of negative 7. And the sigma is 5.8 times 10 power of 7. So when we proceed with this calculation of alpha, we're going to have it as equals to 4 pi multiplied with 5.8 multiplied with 60 multiplied with pi. So square root for this will give us 117. Yeah, 117. And from here, we can see that the skin depth shall be equals to 1 over alpha, which is 8.53. Yeah, 8.53 times 10 power of negative 3 meters. So that should be the skin depth when your frequency of wave is at 60 Hertz. Okay, let's have a look for the alpha value when we are using a 6 gigahertz frequency. So alpha will give us set of pi f mu sigma. So pi f is 6 gigahertz, 6 times 10 power of 9 Then we have the 4 pi times 10 power of negative 7 and 5.8 times 10 power of negative, 5.8 times 10 power of 7, yeah? Okay, so let's have a look at the value for this alpha. So we're going to have it as, sorry for that noise, yeah? Sorry for that noise. For pi times 5.8 times 6 times 1, okay, and then multiply with pi, so that will give us 1.37 times 10 power of 12 and square root the value. We're going to have it as 1.17, yeah, 1.17 times 10 power of 6. Yeah, very huge, yeah. Alpha is very huge, and from here we can find out that the delta or the skin depth, which will be 1 over alpha, shall give us 8.53 or equals to 0.85 times 10 power of negative 6 or equals to 0.85 micrometer. So this is 8.53 millimeter. So we can see the difference, yeah? The skin depth for different frequency wave. So for 60 Hertz, the thickness, the depthness, the skin depth is only 8.53 millimeters. But for 6 gigahertz, the skin depth is very small, which is about 0.85 micrometer. So from here, you can determine, as I mentioned before, if you want to design your device or your system, such as you want to prohibit any penetration of wave. So that's how you can play around with the value of this alpha of your medium. Okay, right. So I think we have done with this example. And for this next example here, I think I don't have to proceed with this because this is about similar, yeah, the method is similar to what we have discussed before, which is to find the phase and amplitude. Basically, this is to be based on calculation of alpha and beta, and afterwards find the amplitude and also find the phase of the E field wave, yeah. Okay, again, I want to apologize for that noise. Yeah, there's the problem with piping in my house, so the guy is doing something with the piping outside my house. Sorry for this interruption. Yeah. Okay, so I think that's done with the wave propagation in good conductor. All right, so I think we have done with the these topics of a material with in a material. So we're going to come up with the last topic, final topics of this EMT lecture, which will be on the wave power calculation. So basically, it's very important for us to calculate the wave power, yeah, the wave power, because might be important for us to know whether the system that we design is it fulfill, yeah, is it fulfill the requirement that we have set earlier in our system design. Yeah, so that's the importance of knowing the wave power for our transmitted wave. Yeah. Okay. So by using a Poynting theorem, yeah, Poynting theorem, which is developed by Mr. Poynting. Yeah, you can find out from the textbook about the Poynting, Mr. Poynting. Yeah, he found out that the wave power can be calculated by this equation. Yeah, the wave power, which is given by the vector of P, is given by the E field vector cross product with the H field vector. So this is the wave power, which is in the units of watt per meter squared. And as we have learned previously, that this can be also used to calculate or to know the direction of your wave propagation, yeah, which is the cross product between the E field wave polarization and the H field wave polarization. So that will determine the direction of your wave. Okay, so from here we can now classify the wave power based on the medium. Yeah, because we have learned from previous lectures that for different medium, the equation of the wave for the E and H will be different, right? So due to this difference of E and H field for different medium, you are supposed to get different value of wave power. Okay, so let us start with the lossless medium or lossless dielectric. So these are the equations for the E field and the H field, in which we consider, for this particular case, that the wave is propagated along Z direction. the E field is polarized along X direction, and the H field is polarized along Y direction. Yeah, so this is the concept that we use here. So the E field is written to be like this, while the H field is written to be like this. Yeah, I think we have understand this earlier. And the H field amplitude can be written as amplitude of the E field divided by the impedance. Yeah, this is relationship between the E and H amplitude. So where we have H field is E field amplitude divided by the impedance amplitude. I'm going to have it as this equation. And from these two terms here, the E and H, you can then find the P, which is equals to the E vector cross the H vector. And this particular P is known to be instantaneous. Yeah, we call it as instantaneous wave power, which is a result of the E field wave equation cross product with the H field wave equation, and that should be the equations that we have obtained, supposedly. But it is more common for us to find or to calculate the wave power in a time average based power density, which is more meaningful. Yeah, which is more meaningful. Yeah. So for the time average power density, in which we symbol it as a P average, the equation for the P average shall be based on 1 over the period. Yeah, 1 over the period T, integration from 0 to T of the P amplitude of dt, in which the P basically is the instantaneous wave power amplitude. Yeah, P is E cross H amplitude. So we just use the P that we have calculated from this equation above. Yeah, so when we calculate this value for the P amplitude, we are supposed to get that for the average power for the case of wave propagation in a loss dielectric, the average power simply calculated as the E positive squared, which is the amplitude squared divided by 2 eta. Eta is the impedance. So this is the equation that can be applied in calculating the average power or time average power density for the case of wave propagating in a lossless medium. Yeah, okay. And for the case of lossy dielectrics and good conductors, yeah, this is for two mediums here, lossy medium and also conductor medium, because both are having alpha and beta. The difference will be on the formulations for alpha and beta, and also for the impedance value. Okay, so we have learned that for the E field, it can be written as this. Yeah, we have exponential terms of L negative alpha Z. We have also the beta Z for the phase, and for the H field, it's written to be look like this. Yeah, H positive cosine omega t minus beta Z minus theta, direction of Y. So theta is the impedance angle. For the case of a good conductor, theta will be 45 degrees. Yeah, and that should be the equation where we have relationship between the E and H. Yeah, and for the instantaneous wave power, which is based on the E cross H, so we have the P, the instantaneous wave power will be E squared over eta, and that should be the equations. Yeah, and again, we are interested to find the time average power density, so that we're going to have this equation. So we're going to have 1 over T, yeah, and integration from 0 to T for the P magnitude dt. So when we substitute the P from above into this equation, finally you are supposed to get this equation of E positive squared or the amplitude squared exponential negative 2 alpha Z over 2 eta cosine of theta eta. Okay, so for the case, this is for the case of lossy medium. So for the case of good conductor, yeah, so we can have about the same equation, but we're going to have a negative 2 alpha Z. Cosine will be 45 degrees. Yeah, cos 45 degrees. And we have 2 impedance amplitude. Okay, so please note that the value for the alpha and impedance amplitude shall be based on the formulations for the case of good conductor. Yeah. So this equation can also be used to calculate the average power for the case of lossless medium. Yeah, because for the case of lossless medium, we have learned that the alpha should be equal to 0. Yeah, this is for the case of lossless medium. Yeah, lossless medium, alpha is 0, and also going to have theta equals to 0 also. So for the case of lossless medium, this equation can be further simplified to be average power equals to amplitude of the E field squared divided by 2 impedance value only, which is similar to what we've obtained in the previous slide here. Yeah, so basically you will be given these equations. Yeah, you will be given these equations for the case of lossy dielectrics. I mean the average power for the case of lossy dielectrics. Yeah, and afterwards you can simplify the equations based on the medium. Yeah, so for the case of good conductor, that should be the equations that can be modified, and for the case of lossless medium, this should be the final equation that can be obtained by having this approximation for the alpha and also the impedance angle of theta. Okay, so that are the equations. Yeah, those are the equations that will be very important, particularly for calculating the average power of the wave propagating in different type of medium. Yeah, right. So let's have a look at this example, which will be the final example of this lecture 25. So we are given a magnetic field component of a plane wave, which is given by 0.5 exponential of negative alpha x sine of 2 pi times 10 power of 3t minus alpha x minus 45 degrees in the direction of z. So if you base on this equation, we can distinguish, I mean, we can obtain few information. The first one is wave propagation. Yeah, so wave is said to be propagated in the x direction, yeah, x direction, because we can see that based on this equation here, we have negative alpha x here, so this is wave directed towards x direction. Number two is the wave polarization. So H field is polarized in the z direction based on this in the vector, right? And number three, we can see that the alpha value and the beta value are similar. Yeah, alpha and beta value are similar. Yeah, so when alpha and beta are similar, so we can see that the medium in which this wave is said to be propagating in is a good conductor. Yeah, because we have this, based on this wave equation, the alpha and beta are the same. So the medium is a good conductor. So that should be our assumption, yeah, based on the given equation of this wave. Right, so this has been, I mean, this has answered question number one. Number one asks us about the medium where the wave is propagated. So since we have assumed just now that, or we have been given the alpha and beta are the same, so we can see that the medium of the wave propagated is a good conductor. Okay, that should be the answer for number one. Number two, the frequency of the plane wave. So that should be f, which is equals to 10 power of 3. Yeah, based on this equation, we have 10 power of 3, right? So this is omega. So the f, the frequency is 10 power of 3 in Hertz unit. Okay, number three is to find the intrinsic impedance. Okay, so we can see that since this is a good conductor, so the impedance amplitude shall be based on omega mu over sigma square root. So we have square root of omega, which is 2 pi times 10 power of 3. The mu is 4 pi times 10 power of negative 7, because we are not given any information about the relative permeability. So we just assume that the mu is mu naught only, and the sigma given to be 10 power of 3 down here. Yeah, so this can be cancelled out, and the value for your loss tangent, sorry, the value for the impedance, sorry, I made a mistake for the symbol, sorry for that. My mistake then. So this is the impedance amplitude. So the value for this will be, yeah, so we're going to have 8 pi squared. Yeah, so we're going to have 2 pi multiply with, okay, 2 pi multiply with 4 pi. Okay, multiply with 1 power negative 7. Okay, and square root for this will give us 2.8. Yeah, 2.8. 2.8 times 10 power of negative ohm. Yeah, so that should be our amplitude or magnitude of your intrinsic impedance, and we can say that the angle of the impedance which will be equals to 45 degrees. Yeah, so for this you can see that the impedance value will be 2.8 times 10 power of negative 3 ohm with the impedance angle of 45 degrees. This is for the case of good conductors. Yeah, okay. Number 4, which is to find the corresponding electric field component. We can see that since the the H field is directed in the Z direction, I mean the polarization for the H field is towards Z direction. Wave is propagating in the X direction. So basically, we can say that X shall be equals to E field direction cross product with H field polarization. Yeah. So we can see that based on this, your E field shall be polarized along Y. Yeah? So based on this, we can see that the E field wave shall be equals to amplitude of the E field wave, exponential of negative alpha x, sine of 2 pi times 10 power of 3 t minus alpha x, yeah, minus 45 degrees. So we can just ignore the 45 degrees then, yeah, because we know that the E field and the H field are having phase change of 45 degrees. So 45 degrees has been stated here in your H field wave, so you don't have to put any phase value at your E field wave equation. Yeah, so you're going to have negative alpha x in the direction of y only. And we know that the E field and the H field is related by the impedance value, where we have the E field amplitude over the H field amplitude is given by the impedance amplitude. So from here, we can say that the E field amplitude will be H field amplitude multiplied with the impedance amplitude, in which when we calculate it, we're going to have 2.8, yeah, times exponential negative 3 multiplied with 0.5. So that will give us 1.4, yeah, 1.4 milli. So we have 1.4 exponential negative alpha x sine 2 pi times 10 power of 3t minus alpha z in the direction of y millivolt per meter, yeah, millivolt per meter, yeah, because E amplitude here is 1.4 millivolt per meter. So that should be your E field. Yeah, your E field wave equation. Okay, I hope you understand on these equations for the E field. Basically, it should be the same, except that you need to know the wave polarization and also the new amplitude for the wave. Yeah, the rest should be the same. And finally, is to find the average power of the wave after 1 millimeter of propagation from origin. Okay, so this is to be based on average power equation based on the Poynting Theorem that we have learned previously, where we have in general for the case of lossy medium, O average equals to amplitude of the E field squared exponential negative 2 alpha z, correct, negative 2 alpha z, or 2 alpha x, sorry, 2 alpha x, because we have the wave is directed towards the x direction. And you have cosine of theta eta divided by 2 impedance amplitude. Okay, this is for the case of lossy medium. So for the case of good conductor, yeah, which is reflected by our question just now. So for the case of good conductor, simply we can see that the theta equals to 45 degrees. Okay, and the E field amplitude just now is 1.4. So we have for the case of good conductor, going to have 1.4 squared as the amplitude value. 1.4 milli, yeah, 1.4 milli, yeah, milli. Okay, and exponential negative 2 alpha. X is 1 millimeter, 1 times 10 power of negative 3, cosine of 45 degrees, and 2 times eta amplitude, the impedance amplitude, which is 2.8 times 10 power of negative 3, which has been calculated earlier. Okay, so for the alpha, I hope that you can calculate this on your own. Alpha will be square root of pi f mu sigma. Yeah, so please calculate the alpha value substitute it into this equation, and afterwards you can find the average power after 1 millimeter of wave propagation. So that should be in the units of watt per meter squared. Okay, I hope that's clear on this wave power calculation. So basically it's very straightforward. You only need to find out obtain the related parameters that is required for the wave power calculation, which include the E field amplitude, the alpha value, yeah, the alpha, the impedance angle, and also the impedance amplitude. Okay, so that's how we calculate the average power for this particular medium of a good conductor. Yeah. Okay, so for this example, I don't want to proceed with this example because this is related to a lossy medium, okay, because you need to find out the average power. Yeah, so again, to find the average power, you need to use equation of E field amplitude squared exponential -2 alpha z cosine of theta divided by 2 impedance amplitude. Okay, so for this example, in short, I can see that we are given the loss tangent of 0.12, 0.035, 0.0009, in which this material at frequency of 1 megahertz, 100 and 3000 megahertz are considered to be a lossy dielectric or lossy medium. Okay, so for lossy medium, in order for us to calculate the average power, you need to use a very long equation, yeah, where we have omega square root of mu epsilon divided by 2, square root of 1 plus sigma over omega epsilon squared minus 1. So have to use this equation and you need to calculate the alpha value. Yeah. So all the informations are given here in these questions. So then you need to find the alpha, and afterwards you need to find the impedance amplitude, need to find the theta angle, yeah, based on the given information, and then only you can substitute that into these equations to find the average power. Yeah, the amplitude is fixed, has been given to be 100 volt per meter. So that should be the E positive, the amplitude value, 100 volt per meter. So this is quite tedious in terms of calculation, yeah, but I hope that you have now understand how to calculate the average power by simply obtain the value of alpha, the value of impedance angle, and the value of impedance amplitude by applying the suitable equations and substitute it into these equations to calculate the average power of the wave. Yeah.